Okay, good afternoon, guys. Okay, address muna natin yung mga questions. Sir, chapters 10 to 12 po yung covered sa exam. Yes, yes, yes. Chapter 10 to 12. Pero feel ko mostly dalawang 12, madaling 11, then saktong 10. May nagbago pala doon sa huling exam nyo, no? Ako yung nagbigay ng tatlong questions doon. Tapos, isa lang yung nabigay ni Sir Baguno. Tapos, bali, for the fourth exam, palit naman kami. Ako naman yung isang tanong lang, tapos siya tatlong tanong. Gusto niyang madaanan natin tong relativity. So baka feel ko magbibigay yung dalawa or tatlong tanong. Kaya pala mahirap na. Mahirap ba? Mahirap ba? Seryoso, sige. Ano yung sabihan niyo? Mahirap ba yun ano? Kamusta yung exam? Kamusta yung third exam? Personally, hindi ko po natapos. At tingnan ko nga. Stop share ko muna. Titingnan ko muna yung exam na. Okay, basahin ko nga ito. Tingnan natin kung ano nangyari. Okay, number 1. Guys, number 1. Number 1, madali. Tama ba? I mean, kung nagets niyo yung idea ng Lenz's law, dapat number 1 should be kaya naman. Ay, babasahin nyo lang talaga ng maigi. Mahilig ako sa mga questions na nagbabasa talaga. Okay. And then, number 2. Number 2 is an example in the book. Pero binago ko lahat ng terms, etc., etc. Okay, for number 2, hindi nyo kailangan kunin yung current I. Okay. Lalagay nyo lang siya as I. Madali lang yung conduction current density kasi meron kang Ohm's law, di ba? J is equal to sigma E. Okay? So, makukuha mo na agad si J. Conduction current density. Basically, yung idea ay pagkukunin mo yung ratio ng JD at JC. Sir, nalito po kami kung ano pong gamit ng resistance na kan. Malay nyo pang pagulo lang siya. Pero hindi, magagamit nyo to kasi given ka ng potential, meron kang resistance, and if your material follows Ohm's law, then you can use V is equal to IR. Diba? Tapos magagamit nyo yun sa yung V, pwede mong isulat in terms of E. Pwede pong hindi magamit. Actually, tingnan ko yung sagot. I-discuss muna natin yung exam. Magagamit nga ba siya? Alam ko, ito ay isa yung number 2 feel ko number 2 pinakamadali. Feel ko nag-overthink kayo sa yung ratio wala akong paki kung JC or JD siya. I mean JC over JD or JD over JC. Okay? Okay lang sa akin either way. Ang mahalaga kaya 12.5 points yung 2D, di ba? Nakita niyo yung Sir, kailangan po bang indicate yung direction ng hindi. Wala akong in-specify kung paano nag-ano yung ano. Wala akong in-specify. Well, nagfi-flip yung direction ng mga currents mo, di ba? Kasi may alternating current ka. So, mahirap lagyan yun ng direction. Okay, so no need. Okay, pero kung nagets yun, nakuha nyo naman, already okay. Wait lang, hanapin ko yung sagot sa Chapter 9. Sir, paano po yung sa capacitance? Ay, yung sa... Yung capacitance, mapapataas mo yung capacitance by increasing the dielectric constant in the between the plates of the capacitor, di ba? Na-discuss ko yun nung dating-dati pa. Okay. So, para mapalakas yung capacitance ng isang conductor, i-fill up mo siya with dielectric material sa gitna niya. And then, ayun, you have that. And then, kasi yung final answer dito, yung pag nakita nyo yung ratio between the two, actually, nabigay ko na nga sa letter D eh. Yung ratio ng displacement current at conduction current density is dependent sa resistivity rho, frequency omega, well, angular frequency yun, pero divide mo lang by 2 pi, pero same pa rin, di ba? Scaled by a constant lang. And then permittivity is given by epsilon. Eh, epsilon, makuha mo naman siya gamit yung epsilon r, di ba? Baka nag-overthink lang kayo dito sa question na to, sa number 2. Okay, so ayun, dun siya nakabase. Okay? Wait, hanapin ko yung sabi. Okay, number 3, hindi ko alam sagot dito. Si Sir Baguna gumawa number 3. Nakuha niyo ba yung number 3? Nakuha niyo yung number 3. Hindi po namin alam kung tama. Tapos, ano ba yung number 4? Number 4 nasa libro. Nakita niyo sa libro yung number 4? Ayan. Kung nagtingin-tingin kayo ng question sa chapter 9, makikita niyo sa libro yung number 4. Ayan. Itong number 2, gagamitin yung idea ng parallel plate capacitor na yung potential difference is just ED. ED. Tapos sabihin nyo sa akin na yung DI distance from the two plates. Makukuha po ba namin yung tamang sagot sa 4, sir, if sinunod lang po namin yung instruction na kunin yung divergence curl and etc. Yes. Oo. Kaya ang baba ng points niya. Kasi straightforward. Plug in mo lang sa mga divergence mo. Siyempre, curl mas mahirap. So, ayun. Sa taas siya. Bakit po ang hirap, sir? Yung number 2, hindi talaga siya mahirap, guys. I-revisit. Kaya nga yung title niya is Capacitor Revisited. So, dapat tinignan nyo yung, yung first lesson on capacitors. Tricky lang yung mga tanong. Chris, sabi ko nga sa inyo, tricky lang ako magtanong, pero madali lang talaga siya. And probably, nang kumukuha din ako ng mga tanong sa libro. Okay? Ang pinakamahirap nga na naisip ko is number 1. Kasi kailangan siya ng imagination. Tapos pag nagkamali ka sa isa dun, tuloy-tuloy na yung magkakaskade yung mali mo. Well, joke lang. 2 question pala yung mamamali. Okay, anyway, sige tuloy. Tuloy na tayo. So, that's for your third exam. Yeah. Thumbs up naman kung kita na yung ano. Okay, thank you. Naka-record na, di ba? Yan. Okay, good afternoon again. So, yung dinidiscuss natin kanina ay about your exam. And tingnan lang natin kung ano nangyari last time, no? So, last time, sinulat natin yung mga Maxwell's equations natin in terms of potentials. And so, para masulat din natin sila in terms of charges and currents. Kasi ayun naman talaga yung given in real world, di ba? What do you have when you have a charge and you have a current J? And what does that give you? Okay, and then tinakil natin yung retarded potentials kasi mahalaga sa atin na yung news coming from your charged particles travels in the speed of light. So, hindi instantaneous yung mga bagay-bagay. So, may mga delay. Therefore, kinuha natin yung retarded potential. Then, hindi na natin dinerive yung iba. Ito si Jeffimenko's equation, which tells you the dependence of the electric field with respect to time, the retarded time, of course, and the magnetic field. Okay? Pero this is very impractical. Sorry. Very impractical. Kasi, tatlong integral, tapos paiba-iba yung vector, and so on and so forth. Mahirap. And then, dinescribe natin na yung moving point charge, meron siyang trail, meron siyang shadow, ganun. When it moves through space, kaya it looks like elongated siya kapag tinitingnan natin, kapag pinifeel natin siya. Therefore, iba yung field ng moving point charge and it is given by the linear Vickers potentials. Ito. Yan. And then of course, arising from this, kapag kinuha mo yung gradient, negative ng gradient ng V, plus partial derivative with time ng A, makukuha mo yung electric field. And we have, tinignan natin yung mga terms dito. Nakita natin na, oops, sorry. Nakita natin na yung terms ay, yeah, two terms. Sir, pwede mo pa-clarify ko ano yung retarded time? Yung retarded time would be the time that kung kailan niya in-emit yung news niya. Okay? So, ito yung retarded time. TR must be equal to yung time mo ngayon minus yung time na tina-travel from you and the point in question. Okay? Okay, so ito yung time mo ngayon. Titingnan mo kung gaano siya kalayo sa'yo. So that's R. curly R, ayun yung, di ba, separation vector. Tapos, of course, nagta-travel yung news by C. Therefore, i-adjust mo yung time mo para makita yung past. Kung ano nangyari yung past. Basically, ito yung kung kailan niya sinend. Kung kailan niya sinend yung chat. Okay, ito yung time mo ngayon. Okay? So, nagba-backread ka ganun. Okay, so yan. Tapos, yung fields ng moving charge ay ito, electric field. Then, you just cross it with curly R hat para makuha yung magnetic field. Then, sinabi natin na this is the velocity field and this is the radiation field. Okay, so first term ay velocity field. So, ayan yung field niya kapag gumagalaw. And then, field niya kapag nag-accelerate. Sir, yung R po ba yung distance at presence? No, yung gusto mong balikan. Yes, of course. Yung babalikan mong distance yan. Okay? So, ito yung itsura niya in real world. 2D lang ito. Ganda sana kung 3D. No? Tapos, ayan. Medyo 3D. Quote-unquote 3D. Okay, that's your field for magnetic field. And then, what happens next? What happens next is chapter 11, reading assignment. So, napag-decidean namin ni Sermon na ito ay reading assignment. So, both classes reading assignment ito. Pero syempre, bibigyan ko kayo ng heads up kung ano ba yung makikita nyo dito sa chapter 11. Okay? Di ba, nakita nga natin from chapter 10 that you have your velocity field and the radiation field. So, in chapter 11, tinitingnan natin ngayon kung ano yung radiation. Radiation is basically the energy that is given off by a accelerating charge that goes to infinity. Okay? So, kapag hindi siya nag-go to infinity, malamang hindi siya the radiation. Okay? Kasi yung mga velocities natin ay yung mga fields natin, di ba? At infinity, they are like yung emo. They are like 1 over r squared. And so, syempre, this vanishes off in the electrostatic to in infinity. So therefore, this is not radiation. Pero kung may acceleration to, makikita natin na yung power, itong electric field pa ng power. So, nagiging 1 over r sila. So, pag in-integrate mo siya, nawawala siya, nagiging linear. Therefore, may something na nakakaabot sa infinity. And that is your radiation. Now, this tells us to think, invites us to think na ano ba yung mga sources natin ng radiation? Paano nag-give off yung mga molecules natin ng radiation? So, titingnan mo ngayon kung ano yung itsura ng mga molecules mo. Di ba nagsabi tayo from chapter 4, yung polarization, tsaka yung magnetization. Ano nangyayari doon? Pag may polarization ka, yung positive mo, and negative mo, naghihiwalay. Okay? So, you have that. And kung iisipin natin, pwede natin isipin na atom ito. Ito ay your proton. This is your electron. And from quantum mechanics, na-observe natin na these two guys, nag-wobble sila. Nag-aano sila. Lumalapit sila sa isa't isa, then lalayo. And so, paulit-ulit. Okay, so, maganon-ganon sila with each other. And that is acceleration. Okay? Kapag nag-stop ka, or nag-go ka, may acceleration nun, di ba? Kaya, yung pagbalik nila to each other and paglayo nila to each other, those are acceleration. And that gives off electric field. Okay? Kung dipole ito. And then electric dipoles. Pero meron din tayong thing sa magnetization, 'di ba, na kapag yung motion ng isang positively charged particle, yan, tapos iniikutan siya ng negative particle. This is also a dipole, but magnetic one, okay? So kapag bumagal siya, therefore, magka-produce siya ng acceleration. Di ba, from quantum mechanics again, nalaman natin na may mga atomic orbital. So, mas mabilis siya kapag mas malapit, mas mabagal siya pag malayo. Okay, so pag lumalapit siya at lumalayo dun sa orbits niya, there is a change in acceleration and that gives off radiation. Tama? Okay. So, tinitingnan ngayon ng section na to kung sino talaga yung main source ng radiation natin. Si electric field ba? Itong system ba na ganito? Or si magnetic field ba? Okay. And kung sa tingin nyo, kung feel ko dapat mahuhulaan nyo na siya ngayon kung sino sa kanilang dalawa. Spoiler alert, si E yung major contributor ng radiation. Kasi kung napansin nyo yung mga electromagnetic waves natin, kanino natin pinangalanan yung polarization? Sa direction ng E. Di ba? Tapos yung relation ng E natin with your magnetic field, it's somewhat like this. Kung speed of light yung velocity niya, E is equal to CB. Therefore, B is much, much smaller than E. Di ba? Kasi scaled siya ng 1 over C. Okay. Amazing, di ba? So, ano ba talaga nangyayari? In reality, this is, well, orbital representation to ng atom. So, nagwa-wobble-wobble siya yung, yung particle mo, yung electron mo, around the nucleus. Kaya siya nagpo-produce continuously ng radiation. Okay? And then, of course, we have to generalize that. You have to generalize that by paano yung formula kapag arbitrary. Hindi mo alam yung source, okay? You just, natamaan ka ng radiation. What would be the source? Diba? So, you have this topics section, radiation by an arbitrary source. Now, syempre, kung tinakil natin yung fields and potentials ng isang point charge, tingnan natin ngayon what happens kapag yung point charge mo nag-accelerate siya to one direction. You have this. Okay, kuwari, this is your charge. Ano mangyayari? So, kapag nag-accelerate siyang ganyan, mag-give off siya ng radiation. Maganda yung graph nito, guys. Basahin nyo siya. Amazing. Produce siya na donut shape na radiation. Okay? Pag nag-accelerate siya. And then with that, yung light natin, di ba may momentum siya? Parang na-describe ko sa inyo na may momentum yung light. So therefore, kapag nag-produce siya na radiation, naapektuhan yung velocity niya. Okay? So may braking, radiation braking. Yung brake ay yung brake. Joke. Brake. Yung brake ng sasakyan. Braking. Yan. So, tinatawag natin yung radiation reaction. Okay? So, ayun lang. So, ayun yung summary ng chapter 11. So, kapag hindi mo sinuplayan ng consistent, continuous push si particle mo, si charged particle mo, ano mangyayari? Pag nag-give off siya ng electromagnetic radiation, ipigilan siya nun. Magbe-break siya bigla. Hindi naman bigla. Through time naman. So, babagal siya dahil sa momentum na ini-impart nung ilaw. Yeah. Bongga, di ba? Okay, so that's your reading assignment. Okay guys, nga pala. Magbibigay ako ng prob set pero January pa. January pa yung deadline. Okay lang ba yan? Okay lang ba yan? Thumbs up pa kayo ko. Tapos ano na lang sila, no? Bonus prob set na lang. Bonus prob set na lang. Bali, dadagdag natin yung sa grade nyo kung sumobra, nice. Kung hindi sumobra, ay di pampaligtas ng ibang prob sets. So, mga 3 prob sets yung ibibigay ko. 3. Kasi sabi ko magbibigay ako ng chapter 10 prob set nung isang announcement, di ba? Pero hindi ako nakapagbigay kasi ang dami kong ginagawa sa buhay. Nakakapagod. So, you have that. January na sila ibibigay, pero syempre, as usual, yung mga prob set na to, makakatulong sila sa exam mo. Okay? So, pwede nyo hindi sila gawin, pero pwede nyo rin gawin naman. Tapos di nyo muna isulat para matulungan kayo sa pagre-review nyo. Alright. Now we go to chapter 12, which is relativity. Ito na yung ito na yung main event. Okay, so balik muna tayo sa history ng ng relativity. Si Einstein na bother siya dun sa idea nung na yung motional EMF, same lang siya sa result ng induction. Okay guys, di ba nakita natin na yung electromotive force kapag ginalaw mo yung bar ng conductor, tapos nagbabago yung flux. Ito yung lumalabas, di ba? And then yung kapag pinatay bukas mo naman yung magnetic field, yung electromotive force na dumadaan dun sa conductor naman is the same. Okay? Di ba parang, bakit sila the same? So ayun, no, napansin ni Einstein na bakit gano'n, na bakit may relativity, may mga bagay na may relativity sa electromag, tapos may mga bagay na wala. Kapag yung point charge, kapag gumagalaw siya, may velocity siya, meron siyang field na given by the Leonard-Vickers potential. Diba? May ganun siya. Tapos, syempre yung naka-stationary naman, walang ganun. So, hindi sila napagpapalit. Pero dito sa EMF at dito sa motional EMF at saka sa Faraday's law, nansin natin na parehas lang. So, doon nag-wonder si Einstein. Bakit ba ganun? So with that, na-develop niya yung dalawang principle niya. Pero wag muna tayo pumunta doon. Tapos, iniisip dati na yung light ay nagpa-pass through or electromagnetic waves. Nagpa-pass through on some ether. Okay? Ether. So what is that ether? Okay, so ang ether, isipin nyo, di ba meron tayong space? Ngayon tinatayuan natin yung space. Okay. So we make waves, and lahat nung nangyayari sa buhay natin, nasa space natin yan. Ngayon, yung ether ay parang ganun din, but yung laman lang nung universe na yun, yung ether na yun, is waves coming from pure charges, electromagnetic waves. Ngayon, nagsispark lalo yun ng lalong confusion sa electromag. Kasi sinasabi nila na yung speed of light would change depending kung saan ka naka sa ether. So kung yung ether mo, itong space mo, wala spacing, yung ether mo. Kapag gumagalaw lahat to, therefore yung speed of light, if that light is traveling onto that 2D area, mas mabilis siya. Okay? Kapag ikaw ay gumagalaw against that ether. Okay? And then kapag ikaw ay kasabay mo yung ether, dapat mas mabagal yung speed of light. Therefore, bago tayo pumunta sa mga relativity ng mga electromagnetic theories mo, dapat malaman natin kung totoo ba tong ether na to. So anong ginawa nila? Sila Michelson and Morley, gumawa sila ng experiment. Kasi inassume nila na, okay, may ether. Okay, so try natin calculate yung difference nung kapag going against and going with the ether. Okay, so you have your sun. And then you have your earth. Okay, earth. That's earth. Then you have an orbit going around the sun. Okay. Now, your ether, isipin natin yung ether ay, may ether ka. Sabihin natin hindi gumagalaw yung ether for the benefit of the doubt, no? Hindi gumagalaw yung ether. Okay. So, dapat, pag hindi gumagalaw yung ether, tapos gumagalaw yung earth, if it goes through here, yung part na to, mas makakaramdam siya ng wind from the ether. Okay? Therefore, iba dapat yung result dito dun sa result ng speed of light dito. Okay? Tama ba? And dito, dito. Okay, so tinry nila yun. Nag-experiment sila ng maraming beses. Tapos nilakihan yung device nila. And napansin nila na kahit anong mangyari, wala silang nakukuhang significant difference from the speed of light. Okay? So wala silang nakakitang pagkakaiba ng speed of light. Parang na-bad trip sila no experiment. Nagsayang sila ng pera para sa isang null experiment. Pero hindi. Naging foundation yun ng maraming theories. Okay. So kahit wala kayong result na maganda, believe. Believe lang. So sila Michelson and Morley, kahit wala silang na-produce na aligned sa hypothesis nila na may ether, may mga nabuong things si Einstein. So si Einstein, nagsulat siya ng papel. Okay. Nagsuppose siya ng dalawa. Okay. Binasa niya si Galileo. And then binasa niya si Maxwell. Okay. So sa number 1, the principle of relativity, the laws of physics apply in all inertial reference system. Okay, inassume niya yan. And then, number 2, the universal speed of light. Ayan. The same for all inertial observers regardless of the motion of the source. Kasi nga, di ba nakuha ni Maxwell na your C is just 1 over square root of mu naught epsilon naught. So, C is constant. Okay? Kinuha ni Einstein yun without questioning it and then combined it with the Michelson and Morley experiment na oo nga, constant dapat yung speed of light. Then, boom. Ano nangyari? So, what happened? When you're, okay, kapag nasa train ka, di ba, sa LRT ka, try nyo na mag-LRT. Probably naman na-try nyo na mag-LRT. Okay, basta nasa train ka, you're moving in the train. Say, sabihin natin na you're moving at 1 meters per second in the train. With respect to the train, di ba? And nakita mo somewhere in the internet na yung train ay somewhere around 10 meters per second. Okay. So alam mo by yourself that you're moving with respect to the ground by 11 meters per second. Tama ba? And that is equal dun sa mga naisip mong values. That is yung speed ng train. Di ba? Make sense naman, di ba? Speed ng train. Kukombine mo kung gaano kabilis So, 1 meter per second. So, pag tinignan ka ng tao sa labas, you're moving at 11 meters per second. Kasi nakita niya yung train, gumalaw ng 10, tapos ikaw gumagalaw ka ng 1. So, dapat 11 meters per second. Okay? However, nagbago nung dumating sa Einstein. Sabi niya na yung velocity, addition rule, would be like this. Okay? VAC. Ayan, ito yung sinasabi ko. Translate nyo na lang. VAC, VAB, and then VABC pala. Dapat. Okay. So, alam ni Einstein na kahit ano mangyari, na yung velocity of light is the same. Kahit gaano ka kabilis mag-travel alongside with it. Okay? So, kunyari, sabihin natin yung train ay speed of light. Okay? Kasi nasa loob ka ng train, di ba? So, what will be your speed? Plug in natin si VBC as C. So, this will become VAB plus C plus 1. Magka-cancel yung isang C, then VAB. Okay? And then if we are to simplify this further, magiging C, 1 over C. Ay, magiging, multiply tayo ng C both sides. Okay? Both numerator and denominator. Tapos, okay. So, yung denominator, pagsamahin ko na, I just multiply this. So, magiging C plus VAB. And this cancels out. And it tells you that the velocity of yourself with respect to the ground is also speed of light. Pansin nyo, no, kahit gano'n ka kabilis, kahit anong idagdag mo dyan, doesn't matter. You will always be speed of light. Okay? Galing, di ba? Paano kung yung sinasakyan ko is speed of light? Gano'n ako kabilis kung tatakbo ko sa loob ng sinasakyan ko? Turns out, ganun pa rin. Okay? So with that, meron tayong tatlong bagay in terms of geometry and relativity. So itong mga bagay na to ay product of geometry. Okay. So sa relativity, yung simultaneity ay relative lang. Okay? It does not, if it is simultaneous for one person, it may not be simultaneous for another reference frame. Okay, so let's look at this. Okay, kuwari ikaw ay nasa loob, then binuksan mo ilaw, and then what happens? You see that the light reaches the ends of the room at the same time. Kung nasa gitna ka ng room. Okay? However, kapag tinignan mo sa labas, ano mangyayari? Okay, kuwari ito. Ito yung cart. Bubukas ka ng ilaw. Kuwari, dito pa lang nagta-travel yung ilaw. Okay. Yeah. However, yung cart mo mag-move na. Mag-move na siya ng onte. So, yung bumbilya mo nandun pa rin. Pero, yung left na ray mo, mas malapit na siya ngayon sa left end. And the right one, sakto lang. Okay? Kasi nag-move yung cart mo to the right with some velocity. Therefore, mahihirapan na abutin yung light nasa right, naabutin yung right end ng trend. Okay? So, ayun, no? Kinuwento niya yan si Einstein sa friend niya, si Michele. Okay? Sabihin, pina-imagine niya yung friend niya na nasa trend. Tapos kumidlat at kumidlat dito. Kinidlatan yung trend. So, ikaw na nasa loob, maririnig mo siya at the same time. Pero pag tinignan siya ng nasa labas, yung isa, mas maaabot, yung light coming from the front end, mas malapit, mas mabilis tatama sa'yo than the light coming from the back end. So yun no, naisip nila na yung pagiging simultaneous it's not the same for all observers. Okay? With that in mind, tingnan natin ano pa yung mangyayaring ibang ibang cases. Okay, so time dilation, balik tayo sa time dilation. What happens in time dilation? Okay, suppose you have a cart, ulit cart, na gumagalaw syempre isang velocity. Pero nasa loob ka ulit ngayon. And then, binuksan mo yung bumbilya. And then, makikita mo yung light going down. Okay. By some height. Okay. H. Okay. So, nakita mo yan. Nakita mo nasa loob. Walang magic, no? Nakita mo siya bumagsak. Okay, how long does that take? Okay, the difference in time would be wait lang, may chat. Okay. Kung tawagin natin itong prime or bar, ito yung mga observations galing sa loob ng trend. Okay? So this is syempre light yung velocity niya, then yung distance na kino-cover niya ay h, then this would be h over c. Tama ba? Kasi this is meters per second, tataas yung seconds. Okay, tama. However, kapag tinignan yan ng isang observer from outside, meron siyang dalawang cases, past, present. Okay, so may bumbilya ka, same position naman. Gawa tayo ng kuwari ito yung past position. Okay. Gawa tayo ng ganyan. Okay. So yung sa past mo, nagbigay siya ng light. Okay, downward. However, so ito yung past image niya. Tapos tatama siya ngayon sa floor sa present. Tama ba? However, kung titignan nyo, kung nasa labas kayo kung papanoorin nyo siya, mapapansin nyo na yung light, it went from here to here. Okay? So that's a longer distance. Okay? Gets ba? Na ito ay madadrag siya, di ba? Madadrag siya pag ano. As your train moves to the right. Okay. So, from the guy outside, mas mahaba yung tinravel nung guy. Okay? Ay, nung light. So, we write that down. The distance covered would be Pythagorean theorem. This is h pa rin. And this length is kung gaano kahaba yung tinravel nung cart. Okay, so this is square root. Tama ba? Kasi hypotenuse yung kukunin natin. This is h squared. And then plus the length would be v delta t. Okay? Squared. And if you're going to isolate this to solve for delta t, okay. Dali lang to, no? Madali i-solve to kasi ito-square agad yung delta t squared c squared must be equal to h squared plus V squared, delta t squared. Okay, ma-isolate mo agad si delta t. And you're left actually with, sige, solve natin para hindi naman nakakalito. Okay, delta t squared, c squared minus v squared, tama ba? And then h squared on the right hand side, tama? And then delta t must be equal to h, tapos over square root ng c squared minus v squared, and then I take out c squared. So that gives me h over c, 1 over square root ng 1 over square root ng 1 minus v squared over c squared. Tama? Tama, di ba? Okay, and what is h over c? H over c is given by delta t bar. Therefore, kita natin na delta t prime, delta t bar is just scaled by 1 over 1 minus v squared c squared. Diba? Okay. And it looks like that yung time sa loob is slower. Diba? Kasi this is always less than 1. And this whole thing is greater than 1. Therefore, it expands this guy. So this guy is greater than 1. Okay? So it expands this guy. Therefore, yung delta t bar mo is a shortened time. Okay? Ayan. So yung moving clocks mo would run slow. Tama? Okay? O ba yan? Ayan. So you have your time dilation na moving clocks run slow. Okay, we have the twin paradox here. So ano ba yung twin paradox? Basically, sir, kung yung paano natin malalaman kung sino gumagalaw? Kung sa titingnan ko yung isang tao, tapos gumagalaw siya to the right, okay. Pag tinignan niya naman ako, gumagalaw din ako to the right. So which one, sino kailangan namin consider? Okay. So in the next few lessons, saka natin malalaman kung paano i-resolve mathematically yung ganong conundrum. Pero eto, tingnan natin yung example ng twin paradox. So may babaeng astronaut, 21st birthday niya. Nag-work lang po yung time dilation, ganyan. Says for very fast speeds kasi kaya hindi to nakita ni Galileo kasi if VA and VAB or VBC are very small compared to C squared. C squared yan guys, C squared. So that's a very large number. This would actually be 0 and would result to this guy. Okay, kaya hindi nakikita ni Galileo yung time niya. Siyempre, wala pang kwenta yung mga physics natin noon. Okay. Ayan. Okay, so ito, example natin would be an astronaut. Yung girl astronaut natin, 21st birthday niya, umalis siya with a rocket ship na may speed ng 12 over 13 times the speed of light. Okay. After 5 years, bumalik siya. Okay? After 5 years ng pagta-travel, babalik siya. So therefore, 10 years ang total travel time niya. Then, ayan. Gusto niya makita ngayon yung twin brother niya. who stayed at home. So, ang tanong ay, how old is each twin at their reunion? Okay, so yung traveling twin has aged 10 years kasi 5 years out, then 5 years pabalik. However, yung pag pinanood siya ng some observer from the Earth, mapapansin nung nasa Earth na yung clock nung astronaut natin is moving very slow. Therefore, yung calculate mo yung gamma, yung constant, ito yung constant, so pinactor out lang, inayos, delta t, gamma, delta t bar. Okay? Okay, with that, inayos yung, tinignan na natin kung ano yung time sa Earth. Ito kasi yung time ng Earth, di ba? So, therefore, kung calculate mo yan, that is 13/5, then times yung time na elapsed doon sa astronaut mo, which is 10 years. Therefore, you get some 26 years. Therefore, yung kapatid niya, yung twin niya, dahil sabay silang pinanganak, 21st din, 21 plus 26, 47 na siya nung pagbalik. So, 31 lang yung babae bumalik, tapos yung kapatid niya lalaki, 47 na. Galing, di ba? Pero walang fountain of youth, guys. Well, yung cells niya bumabagal mag-age, kaya ganun. So, ayan, all biological processes mabagal. Kaya, mas mabagal yung pag-age niya. Okay, so ano yung paradox dito? Yung paradox dito, kasi pag tiningnan to nung babae, nung astronaut, makikita niya yung Earth, lumilipad papalayo sa kanya ng 12/13c. And babalik din sa kanya yung Earth after 5 years. From her point of view, it would seem na siya yung nakahihinto, tapos yung kapatid niyang lalaki, siya yung gumagalaw. Diba? Parang weird nun, diba? Okay. So actually, the math is correct. The math is correct na kapag si astronaut, si astro girl, yeah, kinalculate niya yung time. Mapapansin niya na yung sa traveling sa kapatid niya lalaki, mabagal yung clock ng kapatid niya lalaki kasi nga 'di ba siya yung gumagalaw sa paningin ni babae. Tapos sa kanya normal yung time niya. Pero ang dito, kaya mare-resolve to ng math on the sa later parts ng ating lessons. Pero hindi ngayon to, hindi natin magagawa ngayon. Kasi yung pagbalik mo, 'di ba, may isa kang pag-ganun time, tapos may isa kang pabalik. Okay? A, B. Yung from A to B, okay, kinalculate natin na both sides biglang both sides sa paningin ng both POV, umiikli yung oras ng isa't isa. Pero yung pabalik, may something na nagbabago dun. Okay? Tapos i-consider din natin on the later parts of our lesson na yung length ay nagko-contract. So yung travel mo, yung tina-travel mo would actually be shorter. Okay? Tapos ayun, mare-resolve later on kung paano yung math nun. Mare-resolve siya. Na it would turn out na yung si ate girl, siya talaga yung mas bata kaysa kay kuya. Okay? So yes, no? Parehas nagda-dilate yung time. Ito yung dito, ito yung confusing thing dito. Kahit na kasi sa tingin natin, yung nasa labas ng tao, siya lagi yung siya lagi yung tumatanda ng mabilis, di ba? Pero kapag tinignan mo talaga sa loob nasa loob ka ng spaceship, the same thing would happen. The math gives you the same thing. Ikaw naman yung mas tumatanda. So again, mare-resolve natin yun on the later parts of our lesson. Okay? Okay. Now, Lorentz contraction. Ano mga nangyayari dito? You have your trend ulit natin, then produce ka ng light. Tapos, papunta dyan, then mag-bounce back sa'yo. May mirror ka doon sa kabila. No? May mirror ka dito. Okay? Then, titignan mo kung gaano katagal yung time na yun. Ay, gaano kalayo yung travel. Okay? Therefore, paano ba to? Kukunin natin delta x, titingnan natin. Okay, sorry. Delta t bar. Gamitin na lang natin to. Yung distance mo would be, kuwari ito ay delta x. Therefore, yung travel time from left to right, then right to left would twice. Kung nasa loob ka. Okay. Napansin mo, kasi parang normal yung things sa loob pag nandun ka sa loob. Okay, so speed of light, see? You have that. However, kapag nasa labas na yung nag-observe, napansin niya, ano mangyayari pag nasa labas nag-observe? Magalaw to with a velocity v. And then you have your source of light going from sky and then back. Okay, so nasa labas na yung tao ngayon. So tawagin natin yung time of travel nito as T1 then T2. Okay, for T1, delta T1, that would be delta X plus V delta T, tama ba? V delta T1. Kasi nag-travel pa ito ng some value. So hahabulin niya yun. Hahabulin niya extra. Ay, sorry. May hahabulin siyang extra, kaya may extra term tayo na plus V delta T. Then of course, divided by the speed of light. Tama? And then, delta T2, yung pabalik na time naman would be faster. Kasi itong end na to, yung kabilang end, lalapit na siya ngayon dito. Okay? So, less yung i-cover niyang distance. So, delta X minus yung velocity pa rin nung velocity no train. Okay? Therefore, yung delta T natin, delta T, kapag kinumbine na natin itong dalawang to, so simplify and combine, it would actually be 2 delta X over C. Then 1 over 1 minus V squared minus 1 over 1 minus V squared over C squared. Ang sakit ng ulo ko. Okay? Then you combine all equations. Pagsamahin natin to, makikita mo na if itinry natin eliminate yung delta T, okay? So, i-eliminate mo lang, try mo eliminate yung delta T. Kasi pag in-eliminate mo to, walang sense, di ba? Kasi babalik ka sa time dilation formula. So, ang gagawin mo naman, eliminate mo yung delta T, yung time intervals, para makuha yung length difference. Okay? So, you do that, ang lalabas would be this guy. Okay? So, delta X bar must be equal to gawin natin ay amazingly, ito pa rin yung gamma, di ba? Gamma is 1 over something. Yan. So, gamma, delta x. Okay? Be careful, no? Kasi on the time dilation, nasa left hand yung katabi ng gamma would be the bar quantities. So delta T is equal to gamma delta T bar. Okay? So be careful sa dalawang to, no? So kapag yung objects, gumagalaw siya, very near to the speed of light, it actually shorten. Okay. Given that new, ang weird na tayo, ito yung isa sa mga weird na bagay sa physics. Kung naalala nyo yung field of potential of a moving charge. Di ba sinabi natin na uh, yung mga bagay, they elongate. They elongate kapag tinitingnan mo at some angle, di ba? Ngayon yung point nung last time, di ba? Kaya weird yung field ng moving charge kasi meron siyang expansion na nagaganap. Ay, balikan nga natin. Ano ba yun? Okay, ito naaalala niyo to. Yung kapag tinignan mo yung trend at some nag-expand actually siya kasi delayed yung pagdating ng light sa'yo, sa mata mo. So it would appear that things are actually moving longer. So ano yung mapapansin mo? That one or this one? In reality, ang mapapansin mo, yung yung humahaba. Okay guys? Yung mahaba yung makikita nyo, hindi ito. Pag yung isang bagay is actually moving near the speed of light, it would glow. And streaks of light makikita mo. Ayan. Kaya meron tayong auroras. Okay? Mabibilis yung mga particles na yun. And they would appear as streaks. Okay? Hindi sila very small. They would appear as streaks of light. Okay? So, ayan. Weird lang siya. So, in essence, balik tayo sa Lorentz contraction. Yung moving objects, they are getting shortened. Okay? So, kapag mineasure mo ba sa loob, kuwari nasa loob ka, nag-measure ka. Measure ka na, dala kang ruler. What would you measure? Ang ma-measure mo pa rin is yung kung yung haba ng kung yung haba ng ruler ay end-to-end no train, ay yun pa rin yung ma-measure mo. And kung nasa labas ka, ganun din mangyayari kasi mag-shrink yung panukat mo. Okay? Mag-shrink yung panukat mo. So, sa paningin nung nasa labas, nag-shrink din yung panukat. Pero sa panukat niya, oh, umikli nga siya. Umikli nga siya. Okay? Pero kung may panukat dun sa loob ng train, mapapansin itong nasa labas na umiikli din yung panukat. Okay? So, mayroon din paradox dito sa Lorentz contraction. Okay? Pag tinignan nung nasa labas, mapapansin niya na umiikli yung nakasakay sa train. Nag-shorten yung mga nakasakay sa train. Pero pag yung usapan naman, nandun ka sa loob ng train, makikita mo naman yung mga tao sa labas na nagko-contract din sila. So, sinong tama? Di ba? Kaya nagiging complicated yung relativity. But then again, i-resolve natin yun at the sooner parts of our lessons. Okay, now we have your ayun, tapos na. Transformation. Okay, kuwari nasa isang frame of reference ka. X, Y, and then Z. And then some events happening on okay. Some events happening on E. Happening on that coordinates. X, Z, Y. Okay. Paano ito i-define ng someone that is moving? Okay. So, kung wari yung someone moving mo is a train. 3D na tayo. 3D. Sige, kaya ko to. Mali. 3D yung train. Trailer lang pala. Yan. Okay. So how would this guy denote this event in his own coordinate system? So sabihin natin merong coordinate system si guy na x prime or x bar. X bar. This is your y bar. Then z bar. Okay. How would this guy, how would this person define this event in his POV, sa point of view niya? Okay? Okay. So, sa taong nasa labas, yung taong nasa blue, alam niya yung event ay, yung taong nasa labas, alam niya yung event is happening at X, Y, and Z. Tama ba? And some point in time. Okay? Okay. So, alam niya na ito yon. This is the length of that X, Y, and the height is Z. So, yung event na yun nangyayari dito sa coordinates dito. However, yung coordinates dito sa naka-trend, okay, same yung height. Sige, same yung height and same din yung depth. Kung parehas silang nandito, no, kung nakalapat din yung train sa x-axis na track, kuwari nandito yung train tracks. Okay? Kung doon siya nakalagay, then makikita niya na yung distance niya from that event is also y. Okay? So, y, z, and of course, it's happening at the same time. Therefore, same t. Okay? Okay. Now, mapansin niya yung x-coordinate ng E is somewhat changed kasi nakabase na siya sa x-coordinate ng trend niya. Okay. So, yung trend niya nagsisimula pa dito. Okay. So, yan. Kuwari dyan. Dito nagsisimula yung trend niya. Yan yung trend niya. Okay. Yung trend niya. So, therefore, yung x na ma-measure niya is somewhat reduced. Okay. Depending on the velocity of his train. Okay. So, you have your x to be somewhat changed like this. Okay, so x minus v. Okay, so this is Galilean transformation. This was used by sailors and pirates na okay. Na ganyan siya, moving at the velocity and na mapo-point out ko sa map ko na yung ganito yung dito siya naganap. Okay. Okay. So you have that. So this was before Einstein. Now, ngayon si Einstein dumating siya. Tapos sinabi niya ngayon, paano pag yung trend na to hindi na normal speed? Paano kung sobrang bilis na siya? Ang mangyayari is yung ganap mo, yung mga ganap would be, of course, transformed by your Lorentz construction and time dilation. Okay? Alright. Okay. So yung pansin niyo dito, x prime is now gamma x. Of course, ito rin yan. Contracted lang si x and then contracted din dapat yung vt. Therefore, parenthesis sila. Okay? And then, same pa rin yung sa y and z dahil it's not on the direction of motion. Mapansin mo, yung time nag-change din to gamma t. Okay, sir, di ba parang weird to kasi? So, delta t dapat yung 1 over gamma dapat. Okay? Pero ayun nga, kung titingnan niyo yung derivation nito, it should actually be this. So may extra term ka to correct things. Okay? And with respect to the ground. So hindi ko na sakit na ulo ko guys, sorry. Mag-post pa naman ako, magre-record ako bukas ng lesson to continue this. Sorry guys, nakaya. Ito na lang muna. Pero gets naman yung idea na Kapag nasa ibang frame of reference ka, kunyari, strain na frame of reference, iba yung coordinates mo sa loob. Okay? And you need the language to translate yung mga yung mga walang bar, that is the with respect to an non-accelerating inertial frame of reference. Okay? With respect to something that is moving. All right. We have that. Okay. What else? So, ayun, that concludes the lesson for today. Okay, nagets ba yung time dilation and okay. Parang mahirap siya, no? So, magbibigay pa naman ako lesson bukas. Gawin ko siya on my time. Hey guys, abang-abang na lang din sa sa prob set for 9 and ay sorry, ng 10, 11. Ang bonus naman yung mga yan. Okay, so that's it for today. Sorry guys, masakit na kasi ulo ko. Kaya dito na lang muna. Maganda yung discussions ni Griffiths, guys. Kasi kung hindi kayo, kung di satisfying yung, kung di satisfactory yung explanation ko, then you could, of course, read Griffiths. Masaya naman basahin si Griffiths. Mamimiss niyo si Griffiths kapag hindi na kayo elementary subjects. Hindi ko sabihin elementary subjects ay fundamental subjects. Okay? Kasi pag yung mga PhD levels at master's levels na, ano ba itong pinagsasabi nito? Ba't walang sense? Ba't walang coherence? Walang jokes? Si Griffiths nagjo-joke siya paminsan-minsan. Okay? Any questions? Sorry. Any questions? Any questions? Kung wala naman na. Okay, class dismissed.